Hello everyone, my name is Hangfei Dong from Hanyang University in Korea and my advisor is Professor Simon Song. In this presentation, I'm going to talk about measurement of 3D velocity and turbulent kinetic energy in a refrigerator machine room using magnetic resonance velocimetry. So first, let's see the background of our research. Everyone loves a refrigerator that has high energy efficiency and doesn't make much noise, right? To this end, engineers need a comprehensive understanding of the internal flow distribution and decay characteristics in a refrigerator machine room. As you can see in this image, while there are some 2D model-based experiments or safety studies available, we lack sufficient experimental benchmark data based on 3D velocity and decay. As you know, optical-based techniques such as PIV cannot visualize flow within opaque and complex environments such as the machine room's interior. This is where MRV comes into play. In this slide, I will give you a brief introduction to MRV. MRV is a flow visualization technique that uses a conventional MRI scanner. Unlike other technologies, it measures in a 3D region and is a non-invasive technology, meaning it doesn't require tracing particles. Because MRV uses magnetic field signals for measurement, it is suitable for complex and opaque flow environments. And MRV allowing for measurements to be complete in a short time. Furthermore, MRV can measure a wide range of characteristics, including velocity, decay, temperature, concentration, and Reynolds stress tensor. Therefore, the objective of this research is to visualize the mean velocity and decay in a refrigerator machine room by MRV and provide 3D experimental benchmark data for improving the design of the machine room. In more detail, we aim to measure and analyze the characteristics of the 3D and 3C velocity and decay of a flow in a 3D printed model of a refrigerator machine room. And we wanted to propose an improved geometry with higher flow rate and more uniform flow distribution through the heat exchanger and lower decay. Next, I will briefly explain our experimental setup. As you can see in this picture, I have a closed loop circuit including a pump, an electromagnetic flow meter, a refrigerated and heating circulator, and a data acquisition instrument. For this experiment, we use a phantom, which is a reservoir with a half-scale machine room model placed inside the MRI scanner. To suppress any disturbance caused by the incoming flow to the machine room model, we inserted a flow conditioner to the right of the reservoir. The flow enters from the red inlet, passes through the flow conditioner machine room model, and exits at the left outlet. As a working fluid, a copper sulfate aqueous solution is used instead of air. The flow rate was set to 13.2 rpm to make a Reynolds similarity. Next, I would like to explain the LG mass-produced reference model and compare it to the improved model proposed through our research. First, we changed the direction of the side inlet and outlet to a horizontal position and increased their area by 60%. Next, there was a guide when we looked down from the top of the rear panel and we removed it in the improved model. Next, we plugged the inlet in the bottom panel. And for the sixth modification, we moved the refrigerant pipes to a location with less flow interference. Finally, we relocated the flow blocking parallel. The reason for structure modification will be explained in the research result. From now on, I will talk about the results of the flow visualization. First, I will show you the result of 3D mean velocity measurements. The spatial resolution is 0.5 mm and the number of signal average was set to 4. As you can see, the flow enters from the red inlet and passes through the condenser, fan, compressor, and finally exits from the left outlet. The next result I will show you is a video of the TKE for the reference model taken along the y-axis. Unlike the mean velocity day, the spatial resolution is 1 mm and the number of signal average is 30. Through this video, we can confirm areas where the flow is non-uniform and the TKE is high. And the next is the result of 3D streamlines and the comparison of flow rates through the heat exchanger along y-axis. On the left side, you can see the 3D streamlines for both the reference model and the improved model. Then the red box highlights the heat exchanger zone, where the total flow rate passing through the machine room model interior is constant. The flow rate through the heat exchanger differs for each slice along y-axis. To quantitatively investigate the flow rate through the heat exchanger, we define the ratio of effective flow rate. This is calculated as the flow rate through the heat exchanger zone divided by the total flow rate. As you can see in this graph, it was confirmed that the total flow rate through heat exchanger of improved model was increased by 17% compared to the reference model. And next is the TKE mapping result. As you can see, the reference model, especially at the downstream of the two-stage inlet and the left side of the condenser, showed relatively high TKE. In the improved model, we can see that the area with high TKE are reduced a lot. The right side provides a quantitative comparison of the number of work layers in each given range of TKE between two models, as well as the reduction ratio in the number of work layers. From this table, you can see that the number of work layers with a high TKE range were reduced greater than those with a lower TKE. Therefore, it's probably leading to a reduced turbulence-induced noise. And from now on, I will discuss the changes in flow characteristics resulting from our structural modification. Let's start by looking at the position of plan 1. In the reference model, the inlet angle is direct upward, leading to a non-uniform flow towards the heat exchanger, and there is a large-scale secondary motion resulting in an energy loss. The improved model with horizontal flow direction at the inlet with 60% increase in area shows a more uniform flow distribution and higher speed. Next, we will discuss the effects of removing the guide vanes and changing the position of the flow blocking pillar. Improved model without the guide vanes and the location change of flow blocking pillar. You can see that more flow is direct into the heat exchanger and the lower TKE distribution. And next is the effect of two-stage inlet and one-stage inlet. In the position of plan 1, reference model shows a very high TKE due to the structure of the two-stage inlet. By changing the inlet from two-stage to a single one-stage, we can see that improved model shows a significant reduction in TKE distribution. Next is the effect of refrigerant pipes location. In the reference model, since the refrigerant pipe is located downstream of the inlet, the TKE value is very high. By relocating the refrigerant pipes in the improved model, we can see a reduction in TKE distribution. And here is the result of 2D flow profiles located before entering the condenser for both models. The flow uniformity index, a dimensionless parameter used to quantify the uniformity of flow distribution, is defined as follows. A flow uniformity index closer to 1 indicates a highly uniform flow distribution. The result indicates that the proposed structural modification enhanced the flow uniformity. And so in this study, we successfully visualized the 3D mean velocity and TKE inside the refrigerator machine room by MRV. In the improved model, we proposed the mean flow rate through the heat exchanger increased by 17%, leading to a higher thermal efficiency, and the region of a high TKE value reduced by more than 80%, probably leading to a reduced turbulence-induced noise. And next, in our lab, we have explored several other applications of MRV in engineering flow. First, we applied MRV to the refrigerator freezer. We can understand the flow characteristics inside the freezer and could lead to more energy efficient and low noise designs. And next, we applied MRV to study the flow inside the muffler of reciprocating compressor. A muffler is used to reduce noise. However, when refrigerant passes through the muffler, it experiences additional pressure drop and heat exchange, which can affect the overall performance of the compressor. Therefore, understanding the flow characteristics inside the compressor is very important, and MRV can do it. So this is the end of my presentation. Thank you for listening.